We're going over Descartes Rule of Signs, so I'm just going to do a couple more examples of this. This is from week 5. I should actually label that. And then when we go through these, then if you have a question, or you can type your question, and then we can do that next, so that we can answer what other questions you have. So I'm going to start with g of x. We have 4x squared minus 8x plus 3. So first we're going to look at the number of positive zeros. And that just looks at the number of changes of sign. So we're looking at the number of times the coefficients change sign. And we ignore anything that's a 0. So we have 4, negative 8, and 3. So I'm just looking at the coefficients. So it goes from a positive to a negative, and then we're going from a negative to a positive there. So we have 2 sign changes. And so because it changed signs twice, that means we have 2 positive zeros. Or you subtract 2 and we could have 0 positive zeros. So you always subtract 2 until you get down to 0 or you get to a negative, and that doesn't count. So if we just look at the coefficients, it changed sign twice. So that's 2 sign changes. So that means 2 positive zeros or 0 positive zeros. We don't know which one. We just know that they're going to come in pairs, and it's either going to be 2 or 0. For the negative zeros, you plug in negative x, and then you look at the sign change. You have to simplify. Then look at the sign changes. So we have 4x squared minus 8x plus 3. And so I'm going to plug in negative x instead of regular x. And then I need to simplify. So if I have negative x squared, when you square a negative, you always get a positive. So that basically that negative disappears. Okay, so the negative x, that gives you a positive. So that just stays as a 4. We don't change our sign there. When we have the negative 8 times a negative x, that one changes sign. So now we have a plus 8x. And then we have a plus 3. So now I just want to look at the coefficients, 4, 8, and 3. All of these are positive, so we don't change sign at all. There are no sign changes. And so if there's no sign changes, that means there are 0 negative zeros. There's no other choice. None of them are going to be negative. So that's nice when you're trying to factor, because you're like, well, then I don't even need to bother trying the negatives because none of them are going to be negative. That kind of narrows down your choices, basically cuts it in half based off of our rational zero theorem. Now, sometimes we make a table with this, positive, negative, and then if it's not positive or negative, it's complex. So we know we can have 2 or 0 zeros. We know that we only have 0. There's none of them are negative. Because it's a quadratic, it has to add up to 2. So if there are 2 positive zeros, then that means there has to be 0 negative and 0 complex, because we have to have 2 zeros because that is the degree of the polynomial. It's squared. When we have 0 positive or 0 negative, then your only choice is they must be imaginary zeros. They must be complex because we still have to have 2 zeros. So that's kind of how you fill in the blanks, whether it's positive, negative, or you're going to end up having imaginary numbers. And that helps you narrow things down when you're doing the rational zero theorem, because if you know that they're only going to be positive in pairs, and then once you have like two positives, you don't need to bother checking the rest. It narrows down your choices, basically. Does that make sense?
Okay. Yes, so if the instructions are to find all the zeros, then we know we have to keep checking all the numbers until we have two.
Yes. Yeah.
Okay.
So if it's something that's like x to the fourth, then you need to have 4 of them. And at least it kind of helps you know whether you're guessing with the positive choices or the negative choices. That's where this rule comes into play. Otherwise, you're just kind of guessing randomly and you're just hoping that you're getting there.
Okay.
And I always, when I get down to a quadratic, I always use the quadratic formula, because that's the only way I'd really figured out if there's any complex zeros, because they always come in pairs. There's no way with the rational zero theorem find your zeros if they're going to be imaginary. So in that case, you would have to use the quadratic formula.
I think where I was getting stuck was then the transition from, okay, so we've got this idea of how many zeros there might be, and that they might be positive or negative. The subtract two rule, it's only subtracting 2 one time, right? It's not like if, for example, there were 6 zeros, we'd subtract 2 twice. Could be 6,
yeah.
could be 4,
Could be 2, could be 0, yep. And it's the same thing if they were odd. If you found that there was 5 zeros that were positive, then it would be 3 or 1.
Okay.
When you have our computers these days can like find these zeros and factor these for us, they're essentially using these rules so that they don't have to try every single possibility. You basically have to program a computer so that it follows these rules, so it knows where to start. It saves time and it makes it faster. Because it's like, why do you need to check things if you don't need to? So while it may seem weird that you're learning these rules, let's say someone's going into programming and for some reason you need a program to find the zeros, which actually I had to do when I was learning how to program. These rules actually come in handy then, because it saves you time. Otherwise, you'd just be like guessing random. There are infinite numbers of numbers you can guess. Where would you start?